So now it's the second part. So I assume that you guys plan to brief quote unquote introduction, right? So that now it's a recent developments in the past several years, and so of course it's my work, many collaborators. Maybe I'll have time to mention it again. Okay, so
sorry, your screen sharing pause. Sorry.
Sometimes if you just share it on the desktop.
should I stop?
Yeah,
Yeah.
stop, I'm sure.
Okay.
Share the whole
Screen,
desktop?
Yeah.
So, what should we, where should we start in order for me not to repeat all the previous lecture? Right? So we start with these two equations, which is called the nonlinear dispersion equations. So these are two integral. I'm just saying for those who maybe missed last or something. So these are two integral equations, one for a known function u and the other for a known function b. Equations are independent, right? Okay, and so you can easily see that this is the sort of interaction kernel of the two solitons in the NLS setting. If you replace eta bar by -8, you will immediately set that imaginary bar just to eta. You will switch to KTV setting. Of course, you have to correct this, right? So this, and I will emphasize that this two, with the proper correction, these two equations describe KTV gas as well as focusing NLS. So again, this unknown function u of z, which has to be positive, represents the density of states of the soliton gas. That means that it's average number of average wave number per unit of the spectral, whatever spectral space, wherever it is distributed, and per unit of physical space. Okay, and V is analog in the same analog in the T, so in the T direction. Yeah. So how should I, if I want to transmit this live on Zoom, should I share it on my screen? Will it help?
They show up.
Yeah, I know. Because I've been on the Zoom side. Yeah. Okay. So now the question. So the first question. It's the slide called analysis. So the first question I want to now work a little bit as a mathematician and to ask a question. Okay, what can we say about this equation? Existence of solution, uniqueness, and moreover, we need u of z to be non-negative, right? Because the wave number cannot be negative. That's a big complication because otherwise there might be some tools to say, oh, solution exists, right? But how do we know that it's positive or non-negative? No way. Okay, so so this is I'm reporting mostly my work with Arno at this slides. It's work with Arno Hoovers that was published in Nonlinearity last year. So these equations, if we look carefully a little bit, we see that this part, this integral, is so-called Green's potential for the upper half, right? And that is quite enough of knowledge about this object. So I will therefore denote it by G of mu. where mu, by mu, I understand the measure associated with u of z. So u of z is in a sense should be the density of this measure mu that, and we will be looking for a measure. Okay, so now assumptions that I want to put is that gamma plus is a compact strictly in the upper half plane. Sigma is a positive continuous function. Phi denotes the right hand side, whatever it is, and then we can write this integral equation. Okay. Let's okay. I managed to it. So let's consider first the case. So what is the data for this equation? The data is where we integrate, and that will be developed. That will be denoted by gamma plus. Right. So these integrals are over gamma plus, and I want to again to attract your attention that gamma plus can be a contour or can be a two-dimensional compact set or combination of any combination of the above. We will try not to make it too weird, right? Let's try to stay reasonable. And so that's one piece of input data for these equations. The other is this function sigma, and the rest is whatever is in the right hand side. So three pieces. So the first case, if we take sigma equals to 0, then as it is according to terminology, that is a condensate. And I hope to demonstrate on example how the sort of density, how U becomes the largest possible when we have, in a certain sense, when we deal with the condensate. Then if we introduce this function, so we take this G of mu, which is green potential itself, and integrate it over the support gamma again, minus this term, and call this J0 of mu, and call it green energy functional, which people do in potential theory that is their standard technology. Then we will observe that this equation is the variational equation for minimization of this function. And therefore, so our goal is to find the measure mu that is minimizing this function in the class of negative parallel measures in the upper. And so if we put some assumptions on phi, for example, phi is continuous, that's over too much. The assumption can be weakened, but for us it's good. Then the minimizing measure mu star exists and unique. Right? That's I'm just these are results from potentials. So the minimizer exists and is unique. And well, okay, what about this equation? Moreover, this equation holds almost everywhere on the support of the measure mu star. Right? So mu star, the minimizer doesn't have to be spread all over the compact gamma plus. It can be concentrated in some parts, 0 else. Right. So of course, if it is 0, so this equation can be guaranteed only on the support, and even on the support, it's almost everything. Right. It's I don't go into details. It's quasi everywhere, not almost everywhere, but it implies almost everywhere. Okay, and then in the rest of the support, where in the rest of gamma plus, which is not support of this measure, it would have the same. So it's good that the minimizer exists, but on the other hand, it doesn't guarantee that we have solution to this equation in the standard, in the regular sense. Okay, so. But that's only part of it. The other part is that we want really to consider gases, and that means we should require sigma be non-zero. So we have to insert somehow sigma into the equation. And so therefore the steps that we took to advance this problem is the following. So first we want to modify this energy function so that it will include sigma somehow, right? Because right now sigma is nowhere to be found. And please, if I go too fast or if something is missing, questions are appreciated. So second is that proof that under a suitable condition on all the on all the data involved in the problem, which is compound gamma plus this function sigma and the right hand side by the Euler Lagrange equation, our integral equation holds for all z on the compound, because then we will get solution power. And then clarify the meaning of the density U star of the minimizer and study smoothness of the solution and things like that. Its support of the solution and things like that. Okay, so the first step is the modification of the function. So we had functional J0, right? Or energy functional J0 standard in the potential theory. Now we modify it by an extra term that now it has C. And we will say that our new energy is equal to that if this measure is sigma mu is absolutely continuous with respect to some reference measure lambda. What is this reference measure lambda? Well, it's arc length in the case of if you have some pieces of your gamma plus are arcs, and if some pieces are just regions, so it's usual with that. Right. So lambda is a standard. Is a standard measure. Well, if it happens not to be absolutely, continuous, that is just plus. So that's the functional. And then the first theorem that we obtained is that there is a unique minimizing measure on gamma plus for this energy functional, and this measure. And the measure, if I take this measure mu star multiplied by sigma, it's absolutely continuous with respect to lambda. That is in this sense. It is for some density sigma u star is right. And number two is that this equation, if we take this minimizer, right? So u star is its density, so this equation holds mu almost everywhere on our set. So we got equation solution of our equation, but sort of a weak solution, right? But if we assume additionally, and now I don't know because part of the information.
Click on the slide.
What?
Click on the slide.
Okay. And now if we assume that there is additional constraint, such, for example, the right-hand side is positive, continuous, and superharmonic in the upper half. It's everywhere. It's not only on compact, but everywhere. And really, you can the really constraint here is superharmonic. And I don't go into that. What does it mean? But if it is harmonic, it's okay. For example, in the first equation, we have imaginary eta. That's certainly in the upper half plane positive, continuous, and harmonic. So therefore it works for the first equation, but not for the second, because the condition that positive will be not in place. Okay, so under this additional requirements, then we have equation on outside on gamma plus, but outside of support of our minimizer. We also have equation is satisfied, and we call it weak solution. So where is it not satisfied then? If it's satisfied outside of the support, well, on the support, it's almost everything. We cannot still guarantee that the equation is satisfied there. Okay, so now let's see so the slide I call condensate maximizes the intensity. So let's see what I mean in that. So assume that we have for our integral equation we have three components, as I said. The support gamma plus where the equation should fall, the function sigma, and the right hand side phi. So and I'm sorry, sometimes phi is curly and sometimes it's not. I apologize. I don't know why it prefers to be that way. I apologize. Okay, but so we play this game. We fix gamma plus and phi, but allow sigma to vary. Sigma can be non-negative, continuous and non-negative. Okay. So now we want to show that condensate corresponds to the minimal energy. So how will we say this? Okay, consider the mu zero is a minimizer of the J zero energy for the condensate, right? Okay. So now if we take any other measure, for example, minimizer for the non-zero C, of course, this is a minimizer, so this should be large, right? Obviously. And the next step, okay, but now instead of energy or corresponding to zero sigma, we take energy that corresponds to the sigma pro, right? So we add a positive term. We add this term, right? So clearly it becomes larger, and therefore we have this inequality. So J0 of the minimizer, J0, the minimum energy of the J0 is less than the minimum energy of JC, right? For any C. That's the conclusion. And let's see how to which further conclusions it leads. So if I take this energy, and we know the formula, it's this minus this, so there are these three terms, right, that constitute this energy. Now we combine these three integrals, and we got this expression inside. But remember, the integral equation that holds almost everywhere on the support of this measure is G mu plus sigma density of mu minus phi, right? So if I take away one of phi here, the rest will be integral of the rest will be zero, right? So I ended up just with this one. And now, if you remember that phi is what? It's imaginary eta. Right, and as it will be shown later, this expression is the intensity. It's the average conserved. It's the average conserved density of the NLS solution. Right, so it's average intensity, and that shows that among all the gases, right, with the given parameters, gamma, imaginary eta here, and sigma zero gives you the largest average. Right, so that's it. We can try to push same conclusions for higher conserved densities, but that needs some refinement and understanding. But at least for intensity, it works. Okay. So now I want to move to discuss regular cells. So far we were talking about big solutions, so solution of our integral equation valid almost everywhere in terms of the measure associated of the minimizing measure. But now I want to see when we have solution everywhere. And so we define that. So as you know, as I mentioned before, sigma is a little bit of a spoiler in this equation, because if sigma is positive everywhere, This is the Fred-Hollom equation of type 2. And the existence of solution follows immediately because this integral operator corresponding to this Green's potential is positive definite in a proper functional space, and sigma is positive. So solution is right. Solution is the existence of solution is there, right? Okay. So let's denote by S0 the set of zeros of sigma on top, right? Because sigma, right? Sigma can be zero somewhere and non-zero elsewhere. Right? This is a lot. And so, if this set S0 is of zeros of this function sigma is thick at each of its point, and then we'll also assume, of course, that phi is positive, continuous, and superharmonic, then the equation holds everywhere. In particular, so I will say a few words. What does it mean, thick everywhere? That's again something from potential theory. So this equation holds in particular if the zero set is M, right, for example, or if it is a connected set with more than one point, or a union of such set. So the bad case only is when sigma, when the set of zeros of sigma is just a point or collection. It's if each component of this set S0 contains, if S0 consists of a number of connected components, then we are fine. Right? Then things are good. So what does it and we call such solution there? What does it mean? What does it mean to be thick? So there are definitions, of course, but I don't want to. It will take some time to go into that. So I decided to put here a comment saying that, giving some feeling about that. So take a bounded open set omega, right? The Dirichlet problem for the Laplace equation in this set has a continuous on omega on the closure of omega solution for every continuous function on the boundary, if and only if the boundary is thick at all of its points. So this thickness of all of its points is some sort of a regular behavior of the set, right? In which sense? In this way. Okay. And I also want to mention that the above existence and uniqueness results, as well as the smoothness results mentioned below, can be easily restated for the K derivatives. Okay, so now a few other results. There are more, but I just plugged some. So far I was talking about solution of the first nonlinear dispersion relation with U. There is another with V, where the right-hand side is not, if I continue the right-hand side, which is imaginary of eta square, it's harmonic in the upper half plane, but not positive. So part of the results doesn't hold. So nevertheless, if this function phi is sufficiently smooth, C2 function in the neighborhood of the compact gamma, then equation, the integral equation, nonlinear dispersion relation, has a unique weak solution. And moreover, this solution is regular at every point that is not of every eta that is not a thin point of this set of zeros. So the problematic points are only zeros of this function C, right? If they are isolated or if they form some strange configuration. So this where the problems can be. Otherwise, it's not there.
Alex,
Yeah.
question to that. Intuition, what goes wrong with the one such thing spoils the whole? So
locally, it's point solution locally. Right, it's point solution locally. There will be examples. For example, as you know, even a solution in the case of condensate. So when we work with a normal, so to say, energy in potential theory, the density of the minimizer, if you have like an interval, right? The density of the minimizer blows up at the end. So at the end point, technically doesn't exist. Okay, so then we have a statement that if gamma is a piecewise C infinity smooth curve and sigma is identically zero, right? So it's a condensate, and phi is also sufficiently smooth in some domain containing gamma plus, then the minimizer is a C infinity function on any compact subarc of a smooth arc of. So there are reasons. So if your contour gamma is something like that, right? So solutions will be smooth everywhere except possibly these points that require additional analysis that I have not. Okay, and then there is some lemmas. Okay, what if sigma positive everywhere? What about smoothness? Well, then we can guarantee that this measure not only the minimizer is so U star is the density. U star is the density of the minimizer. So du ds is Hölder continuous on any subarc of. Again, away from the corner. Okay, and if sigma is zero on the smooth subarc, then the density and assuming that everything is C infinity in the problem, then the U star is C infinity. Again, away from the corner.
Can I ask a question?
Yeah.
So when you say it's ds, are you only working in 1D?
Yes. Here it's here is about the story is about. It's I didn't mention, but it's an interesting, pretty straightforward observation that if you have a condensate on a 2D domain, right? Let's say smooth, then it will be zero inside, right? Your solution will be zero inside, and it is. Right, it is concentrated on the boundary. But if you take positive sigma, that's immediately no. Okay, so now what about the kinetic equation? So kinetic equation is again stated it for KdV has this form. So we have density of states, and instead of V, the temporary analog density of states, we take this the function S, which is V over U, and that has meaning of the effective speed of the element of the condensate parameterized with the spectral parameter A. So then the integral equation has this form, and that describes the situation in the equilibrium gas. Equilibrium gas is a gas that doesn't depend on X and T, right, at all. It stays at all points in the physical space. It stays the same everywhere. But we may actually say that the gas in this infinity is different from the gas in that infinity. Of course, should be big scales, and then there will be some dynamics. So this dynamics should be described by this equation, and this equation can be derived if we remember that U of T is some sort of a density of scale Bay numbers, right? And this is U, and V is a scale density of frequencies. But as we know, frequencies and wave numbers, if you go back to the Riemann surface with a lot of with bands, right? They are related to the periods of the quasimomentum and quasienergy differentials P and Q that I described previous time. And it's well known that dTP equals dxq, right? And from here it immediately follows that we have this. So you have to go through the limit, and that will give us this equation. Moreover, assume so technically if we want to consider a dynamic gas, so the support can move, right? For example, endpoints and stuff like that. But if we assume that gamma is fixed, then this equation implies this interesting relation for the so this function is a density of bands, and this is the scale logarithmic length of the bands, and this is the ratio. So you have this these equations for all those quantities. Okay. So now let's a few words for KdV, right? So the equations for soliton gas for KdV were derived in the 2003 paper of Gennady, and so gamma plus was interval in Gennady's work 0, 1, but in fact it can be any set of the any compact of the real axis. Right, and and if we want to connect it to the equations for the soliton gas for the focusing on linear Schrödinger equation, all that you need is to rotate variables 90 degrees by this change of variable, and you will get from NLS gas equations, soliton gas equations to the KdV soliton gas equations. Of course, you have to modify the right-hand side in the second equation. Okay, so therefore, the results, most of them that I mentioned, I didn't mention, or I haven't mentioned, for NLS gas are applicable for existence, uniqueness, positivity, and so on. Okay, so now let's look again at this equation. I put here 0, 1, but it's not necessarily it's any compact of the real axis will do it. And consider the case when sigma equals to 0. So condensate. So this is KdV condensate. Then what happens? And suppose that instead of interval 0, 0, 1, we have n. So we have gamma consists of a number of bands. This is gamma. I give this notation, right? Gamma plus. So that means that this little bands accumulate on big bands, which sometimes I refer to super. Right, and I want to take, so this is gamma plus, I want to take some symmetrical image. If, let's say, gamma plus is on the positive axis, I take symmetrical image to the negative. And then it is pretty straightforward. Well, it requires some work to show that the solutions of this equation for the gas are proportional to the densities of the differentials dp dz and dq dz for this Riemann surface, right? So for this, so it's not original Riemann surface that has tons of little bands. These are surface limiting surface, just finite number of larger bands, super. And so if you take the densities of these differentials, it will be proportional to you and that's again in my paper with Arne in nonlinearity, and therefore these equations ut equals vx becomes this equation, right? Okay, And so what does it mean? So therefore we derive that this differential equation for KdV condensate, right, are in fact, but this equation are well known for people who are doing finite gap solutions to KdV and slowly modulated finite gap solution. These equations describe the motion of this endpoint, right? So this is a KdV rhythm. And so this equation, in fact, is a rhythm equation for the endpoints of J under KdV evolution. And so the evolution would be the same as if you take a finite gap solution with supported on these bands and allow it to evolve according to what it is. Gennady knows a lot about rarefaction waves, shock waves, and all that you can see in the dynamics of the condensate. But now it's condensate. It's not as a KdV solution. It's condensate undergoes this dynamics. Okay, so now let's talk about average. Let's talk about average density. So average density, if you have, so the symbol n means that we are on the Riemann surface with many small bands, right? So this is a Riemann surface where there is n capital shrinking bands, and we take a quasimomentum differential.
To switch to the NLS.
Yes, to the NLS, but it can be KdV.
Oh, that's just slightly different. There is similar expansion.
Yes, because there will be, you can put all, some coefficients will be often zeros, or equal. So it covers both cases. So we have this, this expansion at infinity. And then these coefficients, so the coefficients represent quantities that are conserved under time evolution. And so therefore we naturally are interested to calculate them in the case of soliton gas and in the case of breezer gas as well. Breezer gas, remember, when one of the little band, one of the original bands doesn't want to shrink. It stays. So to this end, I want to say that this sigma zero is associated with this band that that stays constant. So let me switch to the NLS setting. So that there is one band that stays constant, and this is sigma zero or minus sigma zero, maybe I. We'll figure out what it's either I sigma zero or minus. So probably it's positive, so it should be I. Forgive me if I. Okay. And so this numbers is the expansion of this radical Laurent expansion of this radical at phi, and they are related to Catalan numbers by this relation. So some sort of number. Okay, so then the result is that the theorem is that in the thermodynamic limit we have this expression for these quantities. So fix n first. N is fixed. And then let n go to infinity. N capital goes to. Then we have this expression where sigma now is the maximum length of shrinking bands. Right? So sigma goes to zero, maybe very fast. And for the breezer gas, this expression is more involved, where this sign plus means that we take only non-negative coefficients in the Taylor expansion, in the Laurent expansion. Right? That's what this sign. So there is some formula. However, so this theorem, and this is the recent work with my postdoc Fudong Wang that we put on archive. And so the interesting thing, of course, would be when, so that is when n goes to infinity. But if we assume that the counting measures of these centers of the bands are weakly convergent to this measure, right? To u of z d lambda, and u is a solution of the nonlinear, is density of states, which we assume it's there. Then we have, so this sums in the previous slides, the sums here can be transformed into integrals, right? And we have this this formula, for example, that IM equals so it's in general, so therefore there are no zeros or not zeros. So IM is equal to this expression in the case of soliton gas, in the soliton and in the breather gas it is given by that expression. Moreover, if we can even estimate the accuracy, if we know how fast this discrete measure approaches, they can be used. Okay. So now so now when we're armed with that, we can go to the thermodynamic limit of this quasimomentum differentials dPn. So how should I define? What is the limit of this differential? Well, I know the expansion at infinity of dPn. So I just replace the coefficients in this expansion, Imn, with just their limits, just Im. And whatever I get, if it makes sense, I will call the differential, right, of whatever surface I okay. So, but then it's immediate. The first question is a convergent series at all. Maybe it makes no meaning. And the answer is if u or u is a reasonable function, for example, in one or something, then you can argue that this differential is the series is okay. Okay. So in the remaining part of the talk, I consider gamma plus to be a quantum. So I put aside two dimensional collection. Okay. So this is the formula in the case of the solid gas. So now, can we say something more about this object where Im is given by this one? So the immediate intuition that yes, because we have sort of a right, so Im are sort of power series inside integrals in terms of the imaginary part, and then there is another powers. So we may kind of do some summation of this object. And indeed, if we try to do that, so after some calculations that I don't want you to practice, but those who are interested is here, we obtain that dP dz is in fact 1 minus Cauchy transform of object you check or you brief or whatever that is closely related to our u. How is related? Well, you take u on the part of the contour. Here is your contour gamma, and here is u, and then there is some angle of the tangent line. Right, so you factor this angle in, namely the theta is the argument of this vector dz that I wrote, and you get u brief. So that is the relation, and okay, and the details are some details are here. Cauchy transform is written here, so we assume that, of course, Z is away from the contour. Because on the contour there is a jump.
Okay. So what happens in the first line to the imaginary part?
Imaginary part is this, and I take U is anti-Schwarz reflection. So that the integral is instead of gamma plus or
Oh,
yeah. Okay. Okay, so it's good that we have some expression for the limiting differential. Right? Okay, so this is the formula for the limiting differential, dp dz, and in particular, if it is if our contour is if our gas is just a bound state, so gamma is on a vertical line, say the imaginary axis, then it simplifies just to that. Okay, so now I want to dwell on that a little bit more, and I want to introduce the integral of this differential dp, right? And this integral, so think about, so I define the function 2g sub x of z as so its derivative is this differential minus 1. So I should put, of course, n here also, right? So think about this 2g of x as antiderivative of this expression, but this has a limit, then goes to infinity, so that has also. So I'm thinking about limiting g. So the fact that I use g is not random, because if you remember this my last seminar where I introduced g function, stuff like that, it's related. It's actually the x derivative of this g function. Anyway, so then we can calculate. So we just take antiderivative of this, like integral from 0 to z, and we immediately get this expression, which I can work into that expression. So we get that 2g of x. So let's see what is that. It's just a constant term. So this is the value of the function 2g sub x at infinity. And so you see argument of the curve affects, the curve gamma somehow affects this limiting value of this function g sub x in infinity. And this is log transform, but log transform in the complex analysis sense. There is no absolute value. This is okay. And so, and now I want to remind you, before doing next step, I want to remind you that we started in the last lecture. There was this equation related the wave numbers km, right? That were sitting on the bands that were shrinking, and there was second kind of wave numbers which are tilted, and they were called carrier wave numbers, because while those guys were going to 0 as 1 over n, these guys were not. They were going to some limiting values each. And if I go to the thermodynamic limit, this equation will get rise to this equation, right? So then we take imaginary part of this, and it simplifies a lot. So I would like to work with this equation. And namely, this term comes from the breather gas. So let's assume for simplicity there are no breathers, right? So this term is S. And I want to compare this equation with that equation. And you will see that if I fold back, the contour gamma consists in the part of the upper half plane and the lower half plane. If I fold them back, so this logarithm becomes a ratio, right? And I will recover this term of this equation. Now this term in the limit will give me that one. And so what I'm in fact saying that this part is 2g x of z, right? And therefore my equation, therefore I can. So again, what is this function 2g x of z? It has a branch cut. It has a branch cut on gamma, but otherwise it's analytic everywhere else. So if you have a branch cut, of course you are interested in the jump, maybe the jump over, and also average, and also Hilbert transform on this jump, right? So taking average of limiting values from both sides. So if I take this, if I take the sum of the g sub x from both sides, I recover this part of non-integral part of this equation, which is R0. Well, in the case of soliton gas, it will be just C plus U tilde and minus I sigma U of C. So that's what I've written here. And therefore, the interpretation is that the U tilde is a real part of this left-hand side, and sigma U is imaginary side. I didn't put here plus and minus because imaginary side is continuous. There is no jump in the imaginary. So that is the meaning of the integral of the quasimomentum differential dp. Of course, you have the same for dq and for higher. Okay, so I know we started a little bit later, so can I count on at least those minutes there? Okay, so then a few words about periodic gases. What animal is that? What do I understand by periodic gases? Well, take again, you can think different, associate different things, but I mean that. So suppose you have a periodic potential, call it QX. It's for simplicity, I take it to be even, maximum at the origin and the minimum in L, and it goes. So L is half period, and I want it to be one hump, so it's monotonic, right? And I want to consider NLS evolution, focusing NLS evolution of this potential in the semi-classical, right? So that is semi-classical. Then it was calculated by Gina Biondini and Jeff Arigera that the bands of the lux spectrum, so the continuous spectrum then has the form of, so if I draw the spectrum, so this is M minimum, M maximum. Oh, I'm not mistaken. So this is the will be continuous spectrum, this little cross, and the bands, many small bands, will be living in this box of the spectrum. So gamma plus will be that, and this will be part of covered by the breezer, right? That will be the so in the semi-classical limit, right? So this band stays, and then there are many small. So that is example of what is a breezer gas versus solid. So if you have this minimum to 0, then this band shrink, and we have example of solid. Okay, so what can be said about this situation? So first of all, we can calculate the Fouquet discriminant, and it has this form, right? So rapidly oscillating cosine multiplied by cos, also rapid. So what does it mean? It means that there are many zeros of this Fouquet discriminant, right? So you remember the band gap structure is given by, so we take this and suppose this is the Fouquet discriminant, and this is very, let's say, 1 and -1, right? So that will correspond to a, right? So that will be a band, right? Whenever this discriminant is between -1 or something, say -2, depending. Normalization, and then the rest are gaps. So you see that the fact that we have highly oscillatory cosine tells that there will be many bands. They are proportional to 1 over epsilon. They are not. So growing number of bands with epsilon. And when it comes to the size of each, because that grows exponentially fast, so the size of each band should be exponential. So we are exactly in the situation of the soliton. This result is not rigorously established, but the KDV analog is. Right? So for NLS, it's some work to prove this, to prove the error estimate. So in this case, so S1 and S2 are some integrals written here. And based on that, we can derive expression for the density of centers of the bands phi, and there are logarithmically scaled up. So these are the formulae. And so the next theorem tells you that now I can calculate U of Z. And as you see, U of Z is the density of states is proportional to the density of the centers of the bands times a constant. Okay? This is a constant. So I can write it this way. And now I can tell you what means to dilute the gas. So how you can possibly dilute this gas? You can say, okay, I will. So first of all, let's work with solid and gas because time. And so suppose you are in this situation, then you said, okay, I will extend this with from L to KL, where K is a parameter bigger than 1, but just by 0. And then it starts going to the next. So I extend the period, right? Without changing, extended by 0 without changing anything else. Extend by 0. So what effect such extension will have? So my initial potential will have more of empty slots, right? So what the effect will be if you calculate? The effect will be that so this is a diluted gas. The effect will be that then in this formula for you, we just put the coefficient K in the bottom, right? So the larger K, the more diluted, the smaller is the smaller. Okay, and then we also calculated the conserved quantities for periodic gases, calculated the integral of anti-derivative of the differential, and calculated U tilde, sigma U, everything. Then there are a couple of examples for like diluted condensate. Take a constant, then dilute it, then these are phi, nu, and sigma, then other potentials, diluted or not, and conclusions. Thank you, Nina. Right on time. So the conclusions, outlook and conclusions. So conclusions, so what I've reported to you is already probably I will skip, but rather I will mention what are directions that work is going now. So one is KDV periodic gas, in particular Lamé gas, that is joint work with Jeff, Origera, Fudong Wang, and myself. Then thermodynamic limit of finite gap multi-soliton correspondence that I'm discussing together with Marco. And then the special spectral description, going from spectral description to statistical description of gases. That's work with Gennady, L, Tipo, Pongi, Giacomo Roberti, and numerical and physical, sometimes even physical experiments, if possible, are hopefully worked by Pierre, Surya, and Stefano. Thank you very much. Thank you.
Just one crucial question.
No burning question. Do you have any burning question?
No pressure.
on
How crucial the question.
Alex, so that in this theorem with Arnold, you use the properties of the Green's function of the upper half plane, right? Some positivity properties. How much does the result depend on the fact that this is specific to that domain instead of another Green's function, usually for other domains?
I hope it will not be very specifically related. Clearly, if you rotate upper half plane, but another, I hope that the same consideration can go through, but it's positive definiteness of this. Yeah, of this.
That's probably true for any. So you could have the upper half plane with a slit, or
Okay, thank you very much. Alex is around.